So the important thing to remember from the last example is that every real number is also a complex number, even though certainly not every complex number can be a real number. So with complex numbers, to make them useful and interesting, we can extend the traditional operations of addition, subtraction, multiplication, and division to complex numbers. Here are some formulas which I do not want you to memorize, but just to show you how to add complex numbers. We just basically add their real parts and the imaginary parts. It's like if you can add polynomials, you're just doing this, and instead of an x, you have an I. So to add, you just collect like terms. So a plus c, that's the real part. B plus d is going to be the imaginary part. And multiply that by I. Similarly, if you subtract the real parts and the imaginary parts. Multiplying, things are a little bit more complicated, but not too much. Basically, if you FOIL this out, you'll get AC plus BCI plus ADI plus BI times DI, which is the same thing as BD squared. But remember, I squared is -1, so that's why we have a minus BD here. Then we collect the real parts and imaginary parts like we did before, and we get something plus something times I. And it's just important to realize that this is real and this is real. So we have a real number plus a real number times I, so it's a complex number. Division, we're not going to do any division at all in this course, but just to show you can divide them, and the expressions are going to be a little more complicated, but you still get a complex number as long as this bottom complex number is not 0. I'll just say, if you wanted to check this for yourself, we do a trick of multiplying and dividing by c minus di. Okay, and then multiplying things out. So if you want to check this on your own, that's how we do it. So rather than memorizing these, let's just go and just compute these directly. 3 plus 2i plus 6 minus I. You just take the real parts. 3 plus 6. 3 plus 6 is 9. And 2i minus I is 1i. So this would be 9 plus I. For this, if we multiply these out, let's FOIL them. 3 times 6 is 18. 3 times minus I is minus 3i. 2i times 6 is 12i. And then 2i times I would be minus 2i squared. But just remember, I squared is minus 1. So this is going to be a plus 2. So this should be equal to 20, because we have 18 plus 2 is 20, and then we have negative 3i plus 12i, that's plus 9i. Now we can also multiply a square. We can raise something to a power, that's just multiplying. So when we square this is just going to be 3 squared plus 2 times 3 times 2i plus 2i squared. This will be 9 plus 12i, and then this is going to be 4i squared. And again, this is minus 1. So this is 9 minus 4, that's 5. And then we have 12i here. I cubed is the same thing as I squared times I. I squared is -1, so this is -1 times I. Okay? Or just minus I to the 4th will be I cubed times I. We just found that I cubed is minus I. So multiplying these, we get minus I squared, which is minus 1, which is 1. So I to the 4th is equal to 1. You can check that I to the 5th would be I to the 6th would be minus I, or I to the 6th would be minus 1, I to the 7th would be minus I to the 8th would be 1. So you'll see that this repeats every 4 times, and so in multiple, if you take I and raise it to a multiple 4, you're always going to get 1. And in honor of our wonderful year 2020, you can say a lot of things about 2020, but here we can say it's a multiple of 4, so this is going to be equal to 1. All right, so we can because of these operations now, we can substitute any complex number into a polynomial. If f is a polynomial with real coefficients and alpha is a complex number, then f of alpha is also going to be a complex number. We're just doing the operations as we did up here. And so we'll get a complex number. It might be 0 or it might not be, but if it is 0, then we say that alpha is a complex 0 of f. Okay? And notice, according to this definition, every real number is also a complex 0 because a real 0 is a real number and every real number is a complex number, so that works out. And we have this very important consequence. It's a similar to the factor theorem that we had, is that if f of alpha equals 0, then x minus alpha divides f of x. Now, when alpha is complex, that's the same. The only difference is that this g of x might not have coefficients in real. Most coefficients might not be real numbers. In fact, most of the time it will be a polynomial with complex coefficients. But the important thing is that x minus alpha will still be a factor of f of x.